Welcome to my midterm evaluation presentation. I am Shashin Ravin and today I will be presenting the midterm evaluation for my ME420 individual research project. My research focuses on utilizing ultrasonic cavitation for carbon removal and especially designing for a system to clean industrial chimneys. This project is voiced by Mrs. Elvi Bakmideni. Currently in industrial chimneys, the wall is bonded with carbon deposit over time. To clean them, operators have to completely shut down the unit and send workers inside the manual tools. As you can imagine, this creates many problems. It's fully unsafe due to confined space, toxic gases, and fuel intakes. Also, it involves a long time consuming shutdown and is heavily labor intensive. And this is not a uniform cleaning because this is manual cleaning. And to solve this, I am proposing an automated ultrasonic cleaning system as in this slide. The concept relies on a wall climbing robot chassis equipped with a special cleaning head containing a piezoelectric transducer and a water spray nozzle. The system applies a water medium and the ultrasonic transduction removes the deposited carbon while the robot climbs. So does the actual cleaning work? As you can see in my sketch, the mechanism relies on ultrasonic driven droplet dynamics. We are balancing acoustic radiation force and viscous drag force. This creates a dual action. First, cavitation occurs, where microscopic exploding bubbles physically loosen the dirt. Second, we get acoustic streaming, where the water droplet is physically moved to scrub the surface and clear away the loosened carbon. Before building, I conduct a feasibility analysis, mechanical looking at the free body diagram of the wheel forces. The gripping mechanism requires a friction coefficient greater than 0.5 to support the payload. Operation to keep the robot weight down. The system want to power for continuous operation. So I use a continuous power supply for this. For this cleaning physics, I select the 28 kHz frequency, which is more suitable for tackling heavy carbon deposit, but I have to analyze more about the frequency that find the optimal frequency, remove the carbon particles. During my literature review, I confirmed that acoustic cavitation and streaming are act like the primary cleaning forces. However, because ultrasonic waves experience lack of transport in air, a liquid is absolutely necessary to transfer the energy to the wall. And also, I found that while high frequencies are good for fine polishing, heavy industrial soot requires lower frequencies, around 28 kHz, to generate the high energy shock waves needed for debonding. That brings me to research gaps I identified. The first gap is lack of data on optimal liquid film thickness. Most extreme data not for vertical surfaces. In this case, there is a balance. If the water layer is too thin, cavitation simply fails. But if it is too thick, we just adding unnecessary payload weight to the climbing robot. The second gap is between unknown acoustic debonding threshold, especially for industrial carbon. The literature does not clearly define the minimum vibration energy needed to remove soot. We simply don't currently know the exact acoustic amplitude required to overcome that adhesion force among carbon particle and wall. The final gap is dynamic coupling on curved surfaces. Most ultrasonic cleaning studies are done on static and flat setups. My project will especially determine if the cleaning efficiency when ultrasonic transducer move on a cylindrical surface, not a flat surface. So to resolve these gaps, I have a three-part experimental strategy. To find the optimal liquid thickness, I will run a flow rate variation test wherein the water spray between 50 to 200 millimeter and vertical surface to observe cavitation stability versus gravity runoff. To find the debonding threshold, I will compare the cleaning rate and calculate removal efficiency at various frequencies between 28 and 40 kilohertz. Finally, do test dynamic coupling. I will operate the prototype field test on a curved surface and measure the area coverage rate versus the robot's climbing speed. To execute these tests, I've been developing the prototype in SolidWorks because I can do that experiment physically or using software like ANSYS. These are the part I use to develop it. Uh, Here you can see the design for the wall gripping mechanism. These renders show the gear integrations, the specialized friction rollers, and the suspension mounts required to maintain that crucial friction coefficient of 0.5 that I calculated earlier. Also ensuring the transducer stays perfectly coupled to the curved chimney wall. And looking at the project plan, I have completed the method selection, concept development, and identified the core research gaps. Moving forward, the focus shift to finalizing the prototype fabrication, sample preparation, and moving straight to experimental testing to gather my data. At the end, I do a performance evaluation. And thank you.